Hello, my name is Paul Panay, and today I'm going to give my artificial blood vessel presentation. So, this slide I will explain the objectives and goals. The overall objective is to design an artificial blood vessel that meets the demands of a human heart by finding the overall optimal material. This matters because artificial blood vessels are becoming critical in saving the lives of people. The goals for this project include ensuring that the blood vessel, when created in SOLIDWORKS, will withstand human blood pressure for both normal and extreme cases. We will select a material that has optimal biocompatibility, which in turn will be used in the long term, and also optimizing the manufacturability. So materials, my three materials which are being evaluated found through research are PTFE, which is known for its durability and biocompatibility, nylon. Since they didn't have regular nylon in SOLIDWORKS, for a substitute I used nylon 101. Nylon, which is known for both its strength and flexibility, PEEK, which is strong and rigid, but due to its properties, it is less flexible. The criteria for selecting the most efficient material depended on its overall strength, cost effectiveness, and the simulation results determined from SOLIDWORKS. So, from the simulation results from SOLIDWORKS, I will be examining the both stress and strain for all the materials. So this slide, I'm going to explain the parameters and simulation setup. So the two flow rates I found through research which are going to be applied for the normal case are 5 liters per minute, and for the extreme case, it'll be 25 liters per minute. Also found through research is the normal diameter for a blood vessel, which is 6 millimeters, and I will apply that to the lengths of the 1 millimeter, 10 millimeters, and 100 millimeters. As I previously said, my three materials I found through research as well. So for the simulation setup in SOLIDWORKS, after creating the tubes, to one end of the tube I applied the inlet volume flow, and on the other end I applied environmental blood pressure. After running the flow simulation, I was able to obtain the pressure I was able to obtain the overall pressure from the side I selected for the pressure to be on. So after obtaining that pressure, I was able to run a static study from the given pressure to obtain the overall stress and strain results. So this slide, I'm going to explain my simulation results. PTFE was chosen as the optimal material for artificial blood vessels due to its superior performance in several critical areas. It demonstrated flexibility, allowing it to closely mimic the natural compliance of arteries and maintain smooth blood flow dynamics. PTFE also exhibited the highest resistance to stress and strain, ensuring its durability under both standard and extreme pressure conditions. Its biocompatibility is well documented, minimizing the risk of rejection, clotting, or many other reactions, which is essential for long-term biocompatibility in the human body. Additionally, PTFE is also cost-effective and used in many medical applications, which makes it ideal for the choice for large-scale manufacturing. So nylon and PEK were not chosen due to their limitations compared to PTFE. Nylon exhibited flexibility and strength, but lacked the compliance necessary to mimic the natural behavior under regular dynamic blood flow. While it performed moderately well under stress and strain, it had a tendency to degrade in high pressure environments, which will raise concerns about long-term reliability. Additionally, its moderate biocompatibility made it less ideal for more sensitive medical applications. PEEK, on the other hand, demonstrated great structural integrity under the given pressure as well as the stress resistance, but it, however, was too rigid for the compliance of natural blood vessels. So shown on the right is the nylon and PEEK data. So through these data analysis, I did not pick these two because, as I previously said, they do not perform well. So this slide I'm going to explain the overall graphs for both the stress and strain for PEK. So nylon showed both flexibility and strength, but lacked the compliance needed to mimic natural artery behavior. So it had as previously stated, it had a high tendency to degrade in high pressure environments, and its limited biocompatibility. PEK on the other hand had high durable and stress resistance, but it was too rigid. Additionally, PEK has a high cost, which makes it which makes it not as ideal for high-scale manufacturing. So in turn, as I previously stated for both materials, these make them less ideal than when comparing them to PTFE. So, as we can see from the data for both nylon and PEEK, you can see that PTFE, when looking at the graphs on the right, had a higher strain, which makes it more ideal to use, and as well as the stress. So, for my closing slide, PTFE is the optimal choice for artificial blood vessels due to its superior flexibility and closely mimicking natural arteries to maintain smooth blood flow. It showed promise in both. It showed promise in all the simulation results, which ensures its structural integrity under extreme conditions, as well as its biocompatibility. Additionally, PTFE is cost-effective, and it has high availability, making it ideal for production. So, in contrast to nylon and PEK, they lack the necessary compliance and durability. So, and these are my references for my slides, and thank you for taking the time to listen to my presentation.